We are discussing about least squares line fitting, and as we have considered that we have been given a set of data points, and the form of the model in this case is a line, straight line given in the form of equation y equal to m x plus c, and the error term is defined as the sum of square of vertical deviations of the observed value from the predicted value, which has been given by the equation which has been shown by that pink rectangular box, as you can see there, the equation of E. So, you have to minimize this error with appropriate values of m and c. So, that is the problem, find m and c to minimize this error. So, we can write the expression of error in this form. As you can see here that we have converted this expression in the short form of matrix notation of your data. Just to elaborate that how this representation we get, you see the first instance of data where y 1 and x 1 it corresponds to it, and then if I perform this, expand this term, what you will get as a column vector of y 1 minus m x 1 minus c. Similarly, in the second row you will get y 2 minus m x 2 minus c, and in this way you will get y n minus m x n minus c. So, this is a column vector, and if you would like to take the norm of this vector and take the square of the norm, that exactly will give you this equation, or that is what will give you also this form. You can verify that. So, this is nothing but represented in this short form. So, this error E is represented in a shorter matrix notation as capital Y minus x c, where Y is this matrix, x is this matrix, and c is this matrix. So, this is how this notation has been derived. Let me wipe out these writings and proceed further. So, what E can be, error can be expressed. Now, we have a matrix notation, and as you know, the norm of a matrix can be written in this form, y minus x c transpose y minus x c. Just to explain once again, suppose you have a matrix x or a vector which is represented in the form of a column vector, square of the magnitude, that is nothing but it is a, you understand, it is a scalar amount. So, it is dot product of this vector, or we can write it as x transpose x. It is equivalent to x if it is in the vector form dot product, and in the column vector form it is written in this form x transpose x. So, you get y minus x c transpose y minus x c, that is what relating this. And now, you expand each one using matrix algebra, and then you can perform the multiplications also. So, you will get y transpose y minus 2 x c transpose y, x c transpose x c. Since matrix is a linear operation, so you can perform derivatives everything in the matrix form itself, and you can extend the analysis what we know for ordinary single dimensional variable, single dimensional function cases. So, in this case, if I perform the derivative with respect to c, then we will get these equations. It means that independently you are taking derivative of E with respect to each component of capital C for M and for C, and for each one you will get an expression. So, this will also give you actually a column vector of 2 cross 1 column vector, as you can see here. So, these relationships from here which is established or which can be derived using matrix algebra and their derivative, that in short we have written in this form. As you can see here, this is not related to C, this is a kind of constant term. These are the terms which are related to C. So, from here you get this 2 x transpose x C, and from here you get 2 x transpose y. You can intuitively extend your knowledge of differential calculus applying single dimensional variable or applying those or in ordinary single dimensional functional space. You can just extend them using the matrix notation. You need to practice on that part when you are deriving this in a very short and faster way. Otherwise, you can do it component wise, you will find they have a one-to-one relationships with this kind of expression. So, once you obtain this, then you perform once again the algebraic manipulations with this relation. So, you derive C as x transpose x inverse x transpose y. You can see that actually this is the famous pseudo inverse relationships what we previously also discussed. Just to give you the same picture, that I am trying to fit a model like y. This is approximately I am trying to fit that x C. So, I am trying to get C given y and x. So, these are the given data. So, I will be multiplying y with x transpose. In both the side I will be multiplying x transpose, then C can be written as x transpose x inverse x transpose y. That is why what exactly you have derived here. It is the result of minimization of the error. So, just to expand these relationships in a more granular level of data elements, that means to get a solution of M and C, we can get this form. M can be expressed as ratio between covariance of x y divided by variance. You can see from the structure of C, it is also intuitively it could be understood x transpose y and then the inverse of x transpose x. X transpose y indicates the covariance of x and y, and x transpose x is a variance and inverse put it into the denominator. Anyway, there are simpler way of deriving these relationships by performing partial derivative of E with respect to M and with respect to C and forming two equations and solve for M and C. So, these are the equations we will get. Here y bar and x bar is the mean of x i's and mean of. So, y bar is mean of y i's and x bar is mean of x i's. So, error can be estimated by replacing the value of M and C in that expression. Eventually, you can find that this would come like this. You can express them in terms of variance and variance of x and variance of y and relate them with the parameters. So, goodness of fit, as I mentioned, that any model fitting you should observe this error. It is related to this error, and you can express as a quantity called r square equals 1 minus, as you can see in the numerator, it is the square of error, that is what is E itself. Sum of mean square, not mean, it is square of error only. There is, and in the denominator you have the variance of the observed y. So, it is trying to explain that what part of this variance is explained by this data fitting. So, this is what it compares the variability in the measurements not explained by the model to the total variability in the measurements. So, if it is R square value, if it is very high, then your model fit is good. So, this value should lie between 0 to 1, and you can also express in this way. This R square is related to E. Sometimes it is called coefficients of regression. So, once you fit a model, you should find out also R square, and the value should be quite high, say near about 0.8 or more than 0.8, that would be a good fit. We consider that as a good fit in that case. You should also note that this technique is not rotational invariant, and it fails completely for vertical lines, because if it is really a vertical line, then as you can understand, your aim is going to be almost, aim is, so if it is a vertical line, it is x equal to c constant. So, it should be almost like infinity, y is coming up. So, it is very difficult to get so variance of x is tending to be very small, and m is going to be infinity. So, it will fail in that case. So, there are techniques which takes care of these situations, and also here the objective criteria for fitting model is posed in a different way, and this technique is called total least squares. So, it is suitable for any such situation, whether it is a vertical line or not. Now, in this particular diagram, it has been shown that what kind of error measurement we are considering here. Instead of vertical deviation, rather we are considering the deviation of the point from that line itself. So, deviation means the perpendicular distance between the point and the line. So, those are the deviations, and sum of square of those deviations that define the error. We assume here the line is given in this form, say p x plus q y equals d. So, that the normal direction of this line is given p q, that is the property, as you can see. So, the distance between a point and the line, as I mentioned, you have to consider the perpendicular distance, which is algebraically given in this form, p x I plus q I minus d, given p square plus q square equals 1. So, you have to consider that representation where p and q are related with this form p square plus q square equals 1, that you can make always in your straight line equation by choosing appropriate d or scaling them. So, the error is given in this form p x I plus q I minus d whole square, and if I perform the derivative with respect to d, then we get this quantity, and the solution what you get d equals p x bar plus q I bar, and then the error can be written in this form. Now, it is basically a function of p and q by replacing d there, and the constraint is that p square plus q square should be equal to 1. So, we have to choose that p and q which will minimize this error e with the constraint that p square plus q square equals 1. That is the problem that you need to solve. So, once again we can use the matrix notation to represent the square of error, sum of squares in this short form. That means, it is a norm of this particular vector. So, just to elaborate once again, just that you can see that if you consider the first row, it is giving you p into x 1 minus x bar plus q into y 1 minus y bar, and in this way you consider each row is formed. So, the last row is p x n minus x bar plus q y n minus y bar. So, this column vector, and then if you take its norm of square, so you get this expression. So, this is how it is representing in this form, and you would like to make E equals 0. We would like to get a solution, but this can be expressed also. This is this form is, it is u, and this is considered n. So, we are representing as u n transpose into u n as we did for the quadratic expressions in the previous case. So, this is how this short form is explained, and let us continue with this representation. So, as I mentioned, this is u, this is n. So, we need to solve this problem to minimize this error by choosing appropriate n. So, if I derive E with respect to n, we get these relationships that u transpose u n should be equal to 0, subject to the magnitude of n, which is p and q, should be equal to 1, because that is the constraint we have put. As you can see now, that actually this is giving you a set of homogeneous equation. And in fact, if I consider u transpose u as a matrix, then this is the 0 vector of this matrix. So, you have to find out the 0 vector of u transpose u. You can do it in various ways. So, one of the way could be that if you perform if you compute the eigenvectors or eigenvalues, there will be one value which should give you the 0, but ideally it should give 0, but because of the measurements, because of noise etc., you should consider that eigenvector which corresponds to the smallest eigenvalue of the matrix u transpose u. So, that should be your solution in this case. So, this is what eigenvector of u transpose u corresponding to the smallest eigenvalue that you should consider. We can understand this result in a more by applying our notion of geometry, as I have summarized the analysis, and you can see that the direction of normal is given that n is actually in a perpendicular direction of the line what you have fitted here, and in the form of p x plus q y equals d, d is the interpretation of parameter d is it is the perpendicular distance from origin to that line. U transpose u, the structure of u transpose u is also interesting to note. You can see that it is a 2 cross 2 matrix, and whose eigenvalues, there will be 2 eigenvalues, and you have to choose the minimum eigenvalue, and the vectors would be also of dimension 2 cross 1. And the diagonal elements are the variances of x coordinates and y coordinates, whereas off diagonal elements are covariance of x and y, and this is a symmetric matrix. So, this is what once again eigenvector of u transpose u corresponding to the smallest eigenvalue, that is the solution of this problem. Let us now consider the problem of line fitting when you have a situation where there are cluttered observations or there are some outliers in your observation. In fact, this technique, though we will be discussing with respect to line fitting, it provides you a general framework for model fitting in the presence of outliers. You can apply this technique in our previous cases of finding homography matrix or fundamental matrix or projection matrix, those we discussed in our previous topics. So, outline of this technique is that you should choose a small subset of points uniformly at random, and then should fit a model to that subset, then find all remaining points that are close to the model and reject the rest as outliers, and do this many times and choose the best model. So, this is what this technique will be considering, and this is what is used, or general line of approach we will be discussing with respect to a straight line for solving this. So, let me give you a general outline first here, let me explain it. So, the approach what I mentioned earlier, that consider you have a set of points which you require to fit in a straight line. There would be some points which are also deviated and which we consider their outline. So, you may consider, say, this could be a good fit of a straight line among these points. But if I apply the least square error method, the outlier will cause providing you a straight line which is not really fitting this one. It may come something like that, which will minimize the least square error, which is not desirable. So, your objective is to first find out a set of reliable points which we call inlier points, and then apply model fitting on those points only. So, in that case what you are doing, once again use that examples of some of the points which forms a good inlier points for fitting a straight line, and say there are 2 outlier points. And as I mentioned, so what you consider here that you may choose take some initial set of points, arbitrarily choose any set of points. Say initially you have chosen this point and say this point minimally, and then you can fit a straight line, and then you find out how many points which are lying in vicinity to these straight lines by looking at the perpendicular distance, and give a threshold to declare that they are lying in the outlier. They are lying as an inlier point to that model. Now, if this number is quite high, then you can say that no, this is a good model, and then again no, use all those additional inlier points to refine the fitting of your model. But as you can see in this scenario, there are only say 2 points, additionally 2 points, only 4 points, and I mean you can set your parameters in such a way which can decide that this is not a very good fit. So, we will try another set of points. So, let us consider now that you have chosen say this point and this point, and this is your randomly again you are choosing, and this is giving you a initial set of inlier points, and then again you perform this test. That means, you are finding out which point are lying closer to this line, and by computing the distances, and you consider all the points which are outside these lines, that is outside this threshold, they are outliers. So, now you can see at least you can get a good many points within this straight line, and if this number is high, then you may choose this set of points as inlier points and refine your model. So, unless you get a good set of inlier points, you can go on doing this trial, go on doing this operation n number of times. That means, more number of times, and maybe after certain n, if you do not get in any trial there is a good set of inlier points, you may drop the idea of fitting this model, because it may happen the data is not good enough for fitting the model. Otherwise, if you get a good set of inlier points, then you can simply use them and refine your model. So, we will elaborate this process in the next lecture. For the time being, let us stop here, and thank you for your attention.